Welcome back to our series on multivariable calculus. In this episode, we'll be talking about planes in 3 dimensions. When you took Algebra 1, you learned that the standard formula of an equation for a line was ax plus by equals c. Because this represented a 2D line, it might make perfect sense that if we simply expand this to 3 dimensions, ax plus by plus cz equals d, that this might in fact make a line in 3 dimensions. But unfortunately it doesn't. 3-dimensional lines are actually quite complex and will be the subject of our next episode. What this actually is the equation for a 3D plane. Let's go through the derivation for this right now. A plane in 3 dimensions is actually a pretty complex structure. It doesn't really have a fixed direction. Instead, it spreads out in 2 directions. And remember, it's in 3 dimensions, so it could be angled in any way. Because of that, there's really only 2 reliable directions. A plane defines an upward direction, which is everything perpendicular to its surface going up, and everything perpendicular to its surface going down. If it was in a different orientation, those 2 sides would still be there, perpendicular to its surface, either above or below its surface. Well, we know that 2 vectors that point in opposite directions really have the same set of direction numbers. The only difference is they are multiplied by -1. So we're going to treat both of those vectors as if they help us define this plane. Any vector perpendicular to the surface of a plane will be useful to us. I'm going to draw that vector in, perpendicular to this surface, that is meeting it at a right angle, and it has a special name. It's actually called the normal to the plane. And a normal to a plane is a vector that is perpendicular to that plane or surface. We're going to use the normal to help us define the plane. It's going to act as the direction of the plane. Well, the normal on its own doesn't help. Not only can I move this normal around, but there's lots of planes that are perpendicular to this normal. So it certainly doesn't fix this plane as being distinct or different. So I need something else too. I need a point that actually lies in the plane. I'm going to call that point A, and I'm going to give point A the designation x1, y1, z1. So it will be a specific location in space, and that will be a point that definitely lies in this plane. Now I'm drawing the normal as if it exits point A, and it doesn't have to do that. Remember, the normal can be anywhere within the plane. It's just a convenience for the proof that I'm doing right now that I fixated the normal immediately connecting to point A. Well, we're going to need more than just this specific point and the normal. We're going to need one other point in the plane to help define the plane, and I'll call that point B. And point B will have the designation x, y, z. Point B will be a general point, and we'll use it to derive our formula. What I want to do is I want to connect point A to B with a vector, vector AB. Let's identify the coordinates of vector AB right now, since they're both well defined. From A to B would be x minus x naught, or x1, y minus y1, and z minus z1. And those would be its 3 coordinates for vector AB. Well, there's a property of AB that we want to exploit right now. Because the normal is perpendicular to the plane and vector AB lies in the plane, of course, the normal is perpendicular to AB as well. Let's give the normal a designation. We're going to say it's at coordinates A, B, C. Well, now we can take the dot product between the normal and vector AB, and we already know the answer. Because vector AB and the normal are perpendicular, their dot product will be equal to 0. Well, the dot product between these vectors is pretty easy. AB dotted with the normal will produce A times x minus x1 plus b times y minus y1 plus c times z minus z1. And I know that all that equals 0. So I want to distribute to all three of these sets of parentheses, and then I'm going to collect the positive terms on the left side and all the negative terms on the right side. So that will give me ax plus by plus cz is equal to ax1 plus by1 plus cz1. Notice that the left-hand side is the direction vector times the general coordinates x, y, and z. That's where point B is, and it could be moved anywhere in the plane and retain the coordinates x, y, and z. As long as it stays in the plane, AB remains perpendicular to the normal, and this statement is true. The right side, though, is a scalar. That is, it's simply a number because it's the direction vector times the specific point x1, y1, z1, point A, which we already knew lie in the plane. Because this is a scalar or just a number that we would know immediately as soon as we knew the direction values for the normal and the point in the plane, we can replace it with the letter D. And there it is, the equation for a plane in 3 dimensions. AX plus BY plus CZ is equal to D. As long as we know the direction numbers from the normal vector, and we know a specific point that lies within the plane so that we can solve for D, then we can write the equation for this plane. And any set of coordinates x, y, z that solves it lies completely within the plane. So there it is. I know you had high expectations that the equation for a line would come directly as a result of expanding a 2-dimensional line, but instead we found the equation for a plane. We just want to do one more thing with planes now that we have their equation, and that is we want to draw out a plane and answer an interesting question, which is, if I had a plane in space and I knew its normal, or I at least knew its equation, and I had a point in space, what would be the distance between that point and the plane? Well, clearly, the plane extends out in space, so there are lots and lots of lines I could draw from point P into the plane. But only one of them truly represents the distance, and that is the perpendicular distance between P and the plane. As long as I find that perpendicular distance, that represents the minimum distance between the point and the plane, and that's what distance between point and a plane is defined by, the minimum distance. Well, you might think this would be easy. After all, we can get the direction vector, the normal, directly from the equation for the plane. The problem is that's a general vector that can be located anywhere. Finding the version of it that actually passes through point P, and then further figuring out where that vector might intersect the plane so I could find the distance between these points, that's a difficult proposition. So I'm going to suggest that we go a different direction than that. What I'm going to suggest is that we locate any other point in the plane. We'll call that point Q. And point Q, of course, will satisfy this equation right down here. That is, point Q will definitely be a point that's within the plane. And although this is an equation with 3 variables to it, finding points that lie on it is actually quite simple. After all, if we know A, B, and C, and D, then we can simply try different values for x, y, and z until we get a set that works. The easiest one is to simply set x and y equal to 0, and z then would be d over c. So finding a point that lies within the plane is pretty easy. The next step would be to extend a vector from Q to P. Because we've just found the address of point Q from the equation for the plane, and we already know P because it was probably provided to us. After all, we want the distance between the point and the plane. What we now have is the ability to use the normal. Now, the normal doesn't lie in this position, but remember, the normal is indeed perpendicular to the plane. Its length doesn't have to be the length of that side, and it really doesn't matter if it is or not. If the normal is much longer or much shorter, this still works. Recall that one of the things that the dot product does, if we take the dot product between QP and the normal, is it projects QP onto the normal. That is, it finds the length QP in the direction of the normal, and it multiplies that by the size of the normal. Now, this isn't a standard definition of the dot product, but remember, that's one of the things that dot products do, is they project one vector onto another by finding the length of the first vector in the second vector's direction, and then multiplying that by the length of the second vector. Because of that, I'll be able to find this distance between the plane and P by projecting QP onto the normal, because the length of QP in the normal's direction is exactly the perpendicular distance between the plane and P, which means all I have to do is algebraically solve for that. QP in the normal's direction's magnitude will exactly be equal to the dot product between QP and the normal divided by the magnitude of the normal. So whenever you need to find the distance between a point and a plane, you'll need a couple of things. You'll need a vector that runs from a point in the plane to the point you're interested in, and you'll need the direction numbers for the plane in the form of the normal. As long as you have both those, it's pretty easy to find the distance between a point and a plane. Well, this still leaves open the question of how do we actually find the equation for a line in 3 dimensions? Well, that's the subject of our next episode.